I want you to take a second to really look at yourself. Go on, wiggle your fingers, feel your hair, even pinch your skin to realize that humans are way more than the sum of our parts. Now, one of these key parts, are proteins. Just like how a Rubik's Cube can be arranged into over 43 quintillion configurations, proteins come from an astronomical selection of amino acid chains, each reflecting our DNA. It's these chains that become intricately folded like origami because of electrostatic forces, hydrogen bonds, van der Waals forces, even hydrophobic interactions to mold into diverse structures that are directly related to their functions. But protein architecture is very sensitive. Every bend, coil, or pleated sheet contributes to the final function. And although proteins can do amazing things like help create antibodies, enzymes, and hormones, with great power comes great responsibility. Any sort of protein misfolding, tangling, or mutation can contribute to diseases like Alzheimer's, Huntington's, and even cystic fibrosis. Now see, here's where it gets interesting. For decades, scientists have wondered about harnessing the power of proteins and having a tool to predict the 3D structure and therefore predict the function by analyzing the amino acid chain. And thus, the protein folding problem was born. It would be revolutionary to have this superpower because we could target proteins associated to disease development, enhance medical treatments like chemotherapy and vaccines, even create protein-based biomaterials that are environmentally friendly. The possibilities are immeasurable, and they aren't too far-fetched either. Even though methods like X-ray crystallography, NMR, and chiroelectron microscopy have allowed us to distinguish proteins in the past, a more efficient process is needed. This inspired the CASP conference to be brought to fruition in 1994, becoming a top-tier biennial platform for assessing all kinds of protein folding prediction techniques. It was in CASP 13, December of 2018, that the DeepMind artificial intelligence firm developed AlphaFold and made show-stopping progress. DeepMind was able to accurately predict the structures of 25 out of 43 proteins in the novel protein category. The team blended existing protein data and machine learning. They used deep convolutional neural networks. Think of it like a maze with filters, whereas each piece of data traveled through the maze, the filters would organize them to their correct exits out of the maze, or in this case, protein structure information. And the distribution of the data would reveal possible structured proteins. DeepMind fine-tuned AlphaFold more and more by applying the gradient descent technique and solving for the minimal value of the inaccuracy function and inputting more data. The results would be brought to life with the Rosetta software, and boom, we have our protein. It's alive! Talk about a breakthrough. Our imaginations can be brought to life with this biomolecule. Like I said, way more than the sum of our parts. This is Nikita, signing off.